Starting the recording. All right. So today, like the second module, it's a very important topic called model selection, and this is a extremely important like section in this whole machine learning workflow. Okay, so what do I mean model selection? So the main issue we actually covered in the previous session on like polynomial regression and RBF-based regression is, so when you use polynomial regression, what should be the largest degree D you pick? And then when you select RBF kernel-based basis function to do regression, and where do you put the centers, and how many of those kernels you should pick, and how wide. And then even on top of those is, so should you pick polynomial regression or should you pick RBF regression? And then I actually share you even more is this piecewise linear regression. And then which one of the class should I pick? And this is a very important actual question. And then this is almost the question you need to answer as applied machine learning scientist, a machine learning user too. So let's see this is a data you're given. You want to learn a regression function from the data. And let's just consider, I want to try a linear regression. I want to try a quadratic regression. I also want to try this piecewise join the dots linear regression, piecewise linear regression. So which one should I pick when looking at this? Actually, our intuitions can immediately tell us this is actually better. But that's actually humans' intuition, right? So actually try to talk about this. The eyeball, your brain eyeballing the data, naturally you normally know which one is the better one. But what is this eyeball process truly does, and are there some automated way to do this? And to answer this, to solve this, which one does better, and it's really the fundamental question you need to answer. So in this case, why not just choose the method with the best fit to the training data, which is actually this one, right? So why not this join dots version? So the reason is because that's not the answer we're trying to, that's not the correct answer when we are performing the data analytics. And we're not trying to find the best fit to the training data. And what we're trying to do is to looking for a F function that can predict well on the future data. So there's actually an assumption here. How well, we always assume our future data comes from the same distribution of our training data. And what we're looking for is a model that predicts well on the future data that draw from the same distribution as your training data. So let's leave that as the foundation. So this is normally called the RAD assumption. So independent, identical, distributed across the training and testing. So if you do not understand it, don't worry about it. Just think about your testing data will not be too different from your training data. So that's the assumption. So it's a majority of the machine learning method, it's built up actually based on this assumption. So we assume our future data are sampled quite similarly as our training data. And then we look for a predictor that can predict really nicely on those future data draw from the same distribution. All right, so again, let's come back to the generalization. Actually, the definition of generalization, what we give you before, it's a little bit more general than the definition I give you in the last page. So in the beginning of the class, we were saying we want to look for generalization that to learn the function from the past data in order to explain, predict, model, or control new data samples. And actually, in this generalization definition, we don't put that IID constraint here. So, but from now on, actually keep that in mind. Everything we covered, there's, I think, only the RL, like reinforcement learning, doesn't satisfy that IID assumption. Everything else, everything we covered is pretty basic. The basic machine learning all have this assumption. Training and testing follow the same distribution. Okay, now we're grounding ourselves with this distribution, and let's see, because our future data will also be sampled like quite similarly as this training data, right? And then clearly a linear line will not regress them very well. So they're not going to learn the relationship very well, and this linear regression is just too rigid. You can actually tell it's just too rigid. So this is actually called underfitting. So which it doesn't, so my line, this is f function doesn't predict very well on my training data. It also doesn't predict very well on my testing data. And you can think about this is more like the scope of the underfitting cases. And then the overfitting is, so this just perfectly fit my training data, and then I'm having this question like similar sample data. And then it's actually very difficult to tell. I mean, assuming like the FF data here, maybe because that's just more like following the trend, right? So following the trend here. So it seems to be okay in here, but it will perform really badly on this point. So seems like it fits perfectly on my training data, but it actually behaves badly on my testing data. And this is in the regime scope of overfitting. And the good is it seems to be, it has a little bit noise. It's not perfectly predicted, but it's on the future data, the error is still pretty low. So this is what we mean about right. Okay, so now how do we automatically figure out this, I mean, through some kind of computational workflow? So what I showed you in this page is we are selecting from a linear regression, quadratic regression, and also a piecewise linear regression. They are from different kind of model class, right? They're different classes, groups of models. And then even inside the same model class, like in this case, like a polynomial regression, it's all just polynomial, but I do not know this largest D to select. And it also has the similar behavior like the P4. So in using some cases of hyperparameter D, so in this case, D equals to 1, this D equals to 2, and this one D equals to 5. So for some value of this hyperparameter, my model underfit. So both training and testing are bad. For some model, like model hyperparameter like D equal to 5, the training is just perfect. It's just super small training error, but large testing error, future error. And then there's should be something in the middle, and those are the good things. So even for the same model class, I need to select the right D. So this is called hyperparameter selection, which is one kind of model selection. So this is to select hyperparameters. So how do you do it? So we're going to cover two different ways. So the first way we actually know very well. I mean, it's really some training and then split out a held out set, which here we call this train validation split. And there's another kind, it's a more expensive version of the train validation split called k-fold cross-validation split. All right, so let's see what is train validation split. So it's very, very simple. You just split your training data into this part for fitting and this part for, it just held out some sample out, and this is called your validation validation set. And you use this part to do the fitting, and you use this part to do the model selection. So you may a little bit confused now. So if you still remember, we have these two modes of training mode and the testing mode, right? So the training mode is to fit your data, fit your model to the data, and the testing mode is to assess, to know how my data how my model performed on future data. So the correct way actually now, so this is the whole train, but you normally people call this like a train set, and then this called a validation set. And then there's a separate set called testing set. Still the same as we had before, and this is for assessment. So the validation set is used for model selection, hyperparameter tuning. You should not trust the performance on the validation set as your future performance. There should be a completely not touched set of data, which we call testing data, and those are the true part of the future, representing the future to do assessment, model assessment. This is called model assessment, and this is the one you truly report. All right, so train validation test is in fact the state-of-the-art pipelines deep learning normally use. You have a training portion to train the model, optimize, and then you have a validation set to help you do hyperparameter tuning and different kind of model architecture selection. And then there's a total left out testing set is to report the true performance. And this is also like a simulation of all those kind of benchmark competitions. They normally give you train data and the validation data, and they keep the testing data just to themselves, those organizers of competition. And you use your training and validation to get the best possible model, best possible hyperparameter. You submit the model, and then those organizers measure how your model behaved on this completely untouched by anything you optimize, you tuning, and those are the performance. So most leaderboard are the performance on the complete left out testing set. All right, so let's just see how validation set is used to help you do model selection. Okay, so this is very simple. If you have enough training data, to be honest, in this case, we don't have enough training data, but we just show you this workflow, how it looks like. So you left out 30%, and there's only 3 points, because in total, I think this is 10 points. Yeah, 9 points. There are total 9 points, and then we left out 3 points, and we train a regression line, and then on that left 6 points, and then you measure the area on those left out 3 points. And this gives you, you just keep, and this is only one, because you have only one split, right? So this gives you error 2.4, keep that in mind, 2.4. So, and then, so this error is, we actually already reviewed because we are doing a regression task, and then the metric to report is this mean squared error. So on this validation 3 points, you're calculating the error from the predicted X transpose theta y, and then this area, take a square, and then take a summation over 3 points, then 1 over 3, the mean square error is the one you report. So then you perform the same thing using quadratic regression. This actually gives you like still that same 3 points. This gives you a mean square error 0.9, and the same thing, and you fit these joint dots regression models, and then it gives you 2.2. So kind of easy to put them together. We actually know, right, that linear version give you 2.4, quadratic version give you 0.9, and then this dot version give you 2.2, if I remember correctly. Now clearly I picked the quadratic train validation based model selection. So this is extremely simple method, and but there's a little bit issue here is, you left out 30%, right? So which means, so you have only just 60%, actually 70% to train that model. And at the same time, so in this case, I show you, I pick this 3 points as the left out. But in case I'm actually not, it's a random subsample, right? So if I don't pick this 3, I pick, let me see which 3. Maybe I pick this 3 and I left this out. I'm picking a really extreme case. I pick this out too. And there's one more point I pick, maybe this point out. Okay, so let's see what would be this model I'm going to learn. This model will be, oh, actually not too bad. If I do that, yeah, it's hard to tell. Okay, so let me do an even bad version. If I'm picking this point to remove, so what would I get? I think I'm going to get this, and this. Yeah, so this is my revised model, and the error I think will be kind of different now. Yeah, so what I want to show you is just, it depends on what are that 30%, the points you picked. So when you don't have enough training samples, the randomness of that validation set kind of controls what your model selection. And this is actually being observed in many of the state of the art. If you have only the train validation split, and then people just keep trying, and trying, they overfit the validation a lot. Their model actually just behave really, really nicely on this train validation combinations. It doesn't generalize very nicely to the future because, so this type of train test split, really, in most cases, it only fits for super large reference case. Yeah, but to be honest, majority of deep learning workflows are using this train validation test split. The issue is just computational cost. I'm going to talk about the next, because it's much more expensive using the next strategy called k-fold cross validation. Okay, so train validation split, and then a different strategy is when you have not like the super large data, like this millions of data points, and you normally pick this choice, k-fold cross validation. So because this can help you to use all of the data. So every data will be used as once as a validation case. And each data point will be used both as training and validation. So let's see what is k-fold cross validation and what k to pick. So just to give you an example, for example, we use k equal to 10, and this is a very popular k. People use 10-fold cross validation. You just split your data into 10 folds, and you pick one of that fold as, so actually more correctly, this should be called a validation, but yeah, that's fine. It's just because you're going to use it in the testing mode, right? But keep in mind it's actually for validation. So you pick one of the fields to perform this validation, and then using all the rest as the training to optimize to get the best parameter. And you just have a for loop on top of this and loop over all the possible subfield and to use it as one of the validation use. And by this way, you perform K training and K validation testing. So let's look at K-2. And if you think about K-2, it's almost 2 times of the train validation split, what we had in the train validation case. So you have one part, half as training, and the other half as validation to report the error. Then you flipped it. And then the previous train part got be used as the validation reporting performance, and the previous validation is to be used as the training data to optimize to get the best parameter. So it's this. If you look at this, this is already 2 times more expensive than stream validation workflow. And then if you have to do this K field, this is like K times more expensive than the only just one stream validation split. So it's like a super expensive, right? Quite expensive. KX expensive. So how do you report performance? I mean, for each field, you got this validation error, and then you just put all this together, take a summation, then over this K, and this is the cross-validation error you're going to use. You will use this to perform model selection or hyperparameter tuning. And this is used to perform model selection. So again, keep in mind, cross-validation error, it's not the error like representing future, and this is used for do cross-validation, to do a model selection. All right. Okay, so let's see even like more extreme K. I mean, if you pick K equals to N, the number of reference samples, and you're just going to leave one point out, use all the samples as training, keep going, and you're going to do this N times of training and then testing. Let's use our example to show it. So you pick one point, leave it out, and then you learn this regression data, then you put it back, and then to check the error. And then you keep doing this again, to perform this on all the 9 points. And then you accumulating that error or put it together, and this is your leave one out cross-validation error. Okay, so if you have questions, just feel free to ask on chat. Yeah. Very simple. Do the same procedure on the quadratic regression, and then this gives you 0.9. And do the same thing for this piecewise linear joint dots regression. This gives you 3.33. All right, so there's a little differences versus a train validation based error is this type of leave one out cross validation error. It's fixed for given data. So especially leave one out because you leave a data point out, and it's actually it doesn't vary much. But in the stream validation split case, I mean, it depends on what subsampling you use as the validation set. It has a lot of variance there. That error has a lot of variance, and cross-validation error, it's a relatively stable metric compared to the validation error. Okay, so let's compare. So validation set, held out set approach, it has the downside is that kind of that error, that metric, it depends on the subsample of the validation set. It's not as reliable as the cross leave one out type of estimation. But it's super cheap. So I think this is trying to give you one more, like k equal to 3. Let's just go over this. I mean, the question is which k to pick, right? So in this case, it picked 3, so you just leave out, I think in the first phase, you leave out blue. And then in the second phase, you leave out green. And the third phase, you leave out purple. You got 3 points. You got 3 curves, right? Then you report the error. Okay, so now this actually tells you something a little bit odd. So when you have train validation split, you have just one model, you train on the train, you report this validation, you select on that validation. But in the cross validation, you actually got k different models from k different folds, right? Which one should you use? So this is the natural first question. So which one of the model for the k should I use for as my final model to report, maybe to submit to a leaderboard? Yeah, let's just think from this scenario. I'm using k folds cross validation. I'm trying to learn this best hyperparameters, but I got k trained model for that specific hyperparameter if I know that's the best. Okay, you do the same on the quadratic. You also got 3 quadratic lines, and you do the same thing on 3 dotted regression lines. So how do you pick? Let's keep that in mind, and then before we answer that question, let's compare one more time for different k and also versus that validation set approach. The validation set approach, in the end, the best reason to use it is it's super cheap. Computationally, it's cheap. And leave one out is super expensive. It doesn't waste data. But if you have so many data points, only one point out, your model almost has no differences. I mean, it's equivalent to, I mean, you train like this n different models, but they almost the same model. When you have a lot of, in those cases, you have super many reference data. So it seems like there's not much need to do this leave one out. So it's the leave one out, it mostly be used in the smaller training regime, when you have smaller reference data. So it has some kind of weird behaviors. I mean, we'll talk about that later. And for tenfold, it weighs like 10% of the data, but it's 10 times expensive. So in general, it's k-fold wasting 1/k% of the data in the training, but it's the k times of expensive. So let's see the previous question. So you have all those, you have k-folds, and then you calculate for each one of the possible models. Like in this case, can be joined dots, quadratic, degree maybe 1, degree 2, degree 3, all the different model class you select. And you perform each one of them a k-folds cross validation. And then you just put those errors together. It gives you just select the one has the smallest k-folds cross validation error, and this is the model you pick. So this is what we mean, the cross validation based model selection. So for here, I want to do a code run, but before that, I want to skip because I need to change screen. I will cover 2 pages of more like later I'm going to talk about. So what we are trying to talk about today is how to do model selection. But we did not talk why and what's the theorem behind why do you need to do the model selection. And this is actually relevant to this most fundamental intuitions, principles of machine learning. It's this something called variance of a model or bias of a model. So these are like 3 cases we actually give you in the beginning. So we call this is underfitting. So the case of underfitting, it's actually caused by the high bias, low variance model. The high bias issues. And then the overfitting is actually here. And overfitting is actually because your model has too high variance. And we will actually theoretically prove what do we mean whole variance of the model and bias of the model. So I think after k-nearest neighbor, which is the last section of the last class of the first section, and this is about right. So like this has really good. This is about right, and we will show you from the equation at theory level what do we mean this is about right. Yeah, later. Okay, so and we normally have this kind of curve. So this is a very important curve. So when you think about models, and there's a concept called the model complexity, and the model, when it's more complex, it has higher variance. The variance go up. Yeah, so let me cover those later. But this curve, it's important, and also keep in mind there's a differences of model selection versus model assessment. Whenever people talk about leaderboard, and those are model assessment. And let me now change to my code run, which I want to show you, like this. How do you do this model selection from Jupyter notebooks? All right, I think this is, yeah. All right, so this is a code piece I revised from actually this like Python data science notebook, and also there's some errors in this notebook a little bit, so I updated based on the recent scikit-learn updates. All right, so still it's our polynomial regression, which you already remember what it looks like, and in this case, it's just x to the d, and then you try to learn all the theta weights before all this x to the d and d minus 1 onto x, and then plus a bias term. So this is our old like polynomial regression model, which is just a reuse of linear regression, and by updating the feature into a polynomial feature, this feature functions. Again, so that's generating data. This data looks like this. There's like 40 data points here, and it's so clearly that it's not a linear regression can fit this. And this is already shared. You can play with it. And then we already had this last time. We just fit different type of polynomial regression curves. We tried 1, 3, 5, 7. We can also try 7. Yeah, I think I tried 7 last time. Yeah, all right, if we see this big drop like 7, right? All right, so this time I want to show you actually this function called scikit-learn has a model selection library, and which actually you're going to, we require you to implement it in the homework too. So this is how it looks like in this library. So this model selection has a function called the validation curve. And it's just generating the different kind of scores, which is very similar to the one I tried to show you. So there's this, the x-axis in this case is the degree of the polynomial regression. So the more to the right, the more complex is the model, right? So this is, so I'm trying 0 to 21. The largest degree of this polynomial regression I'm trying to fit onto 21. So let's go back to see this. When this degree equal to 7, this is already pretty wild, right? And let's, yeah, this rough thinking is it's not necessary the higher the better. There must be a degree actually, or a range of degrees that's good for my data. So this curve exactly shows you those. And the blue curve shows you the training score, and the red curve shows you the validation score, which kind of echo the last page I tried to show you. So we normally show, try to draw this type of more like a sanity check type of visualization. So in homework 1, you're using training loss versus the epoch type of visualization to check your how your gradient descent converge or not, right? So that's the one type of check. I mean, this the epoch versus training loss curve. And then in the model selection, and this is the sanity check visualization curves you should use. So the x-axis is the model hyperparameter. And you normally just, the left is less complex, the right is more complex. So in this case, so it's the D, right? For polynomial regression, that hyperparameter is the D. So on the left, I'm using like when D equals to 1, it's just a linear regression, right? When D equals to 2 is a quadratic regression. And this one goes to really wild. It goes to even to 20, right? All right, so for each one of that model hyperparameter, you actually plot its training error. In this case, actually, I think it's, I don't remember, it's like fit score or, yeah, because this is a polynomial regression. So I think it's maybe the R2 score, if I remember correctly. It's actually higher the better. So you can actually tell when your model, so this is like when D equals to 5, the training just seems to be perfect. It doesn't, whatever, when you're going more, I mean, when D equals 5, it's already very perfect. And then it goes to, it just kind of plateau. Your training is always, when your model becomes more and more complex, your training error will be smaller and smaller. And also it always just go to a plateau type of shape. So this is the training curve, training score versus the hyperparameter. But your testing or your validation or the cross validation will not look like going to a plateau. It always has some kind of a U shape. So actually in this case it's a reverse U shape. And because this is exactly what I want to try to show you, if you have a degree 7, it just clearly overfit your data. It will not generalize well to the future point. So let's try even more. So I think this goes to 21, right? I can try maybe 15 and 20. Let's see what this generate. So I think 20, wow, look at this 20. This 20 curve, I can even remove the 1, 3 because we know they're good. So let's see, what does the 20 is the green one. So it totally overfits your training data. It goes super, super wild in the boundary cases. And of course, in the validation performance, it should be bad. And this actually very nicely reflected in the validation score when you have higher and higher degree, and the validation performance got really worse. And I think this used the cross-validation, 7-fold cross-validation. So this is a 7-fold cross-validation error. So how do you do feature selection? I mean, model selection. You're trying to pick the point that give me the highest, in this case, because the higher the score, I just do a max operation. And this one gave me the best. And I think this is corresponding to D equal to 3. And the model selection just perform a max operation on the validation, this validation curve, and then pick that best. Yeah, this one is 3, and I picked it, right? So then I use this to retrain. So let me clean up my writing. So this is the model selection. I got that. Then I'm just refit it. I use this best D to fit a data on all of the training. So this includes every training, right? So this is how I got the final model. So we actually talked to you. There's when you have this training, there's the training portion. There's a total leaderboard type of testing portion. You're not going to touch it. Don't touch the test. And then you perform cross-validation to pick the best D. And each of that cross-validation trained only on k-1 fold, right? After you have the best D, you use this best D to train on all the training data to get your final FD star. And this is the one you're going to submit to the leaderboard. So again, cross-validation, it just helped you to do model selection, and then you use the best hyperparameter, best selected models to train all together on the training parts, and then assess the performance on this totally not touched testing parts. Yeah, leaderboard. Leaderboard type, don't touch it, no touch. You should not touch anything in your test data, in cross-validation, in optimization. No, you should not touch especially the labels. Yeah, don't touch the test labels. All right, so this is about model selection, and then use the selected best model to retrain. And I want to show something else. All right, so this is really interesting. So I'm making the same type of data, but now there's a lot more. So this is 200. So let's go back to see the previous data. This is, I think 40. Yeah, so this is 40 in my training data. And this is 200, right? So let me do the same thing as before, this model selection. Totally the same. And the degree, it's also the same. I think it's on 221. You do cross-validation 7-fold. Let's see this. Okay, so on this new data, you also plot training versus the validation. And then this x-axis is the D. And they're solid lines. And blue is the training, red is the validation. And you also call that imprint the training curve and the validation curve you get from that smaller data. So it's actually really, really odd. I mean, the training look kind of similar because on this 200 data points training data, my training curve versus the complexity hyperparameter, it also reaches a plateau. But the score is a little lower. It's a little bit lower score, not as good as the other train. So, but yeah, this actually can be explained, but you need to think a little bit why this is a little lower. And the dramatic differences is the validation curve. So on this 200, so the solid line, the solid is from the training side into 200. And the dashed line is from this training size. The dashed line is from that training size from 40, and the validation portion is 7-fold. So actually the validation size, it's only 7, about 7. Yeah, 6, actually 6. So it's a little odd if you look at this. In fact, I mean, the validation curve doesn't go down. Didn't I say, I mean, when your degree is so flexible, it would not fit very well? It's actually a very, very interesting phenomenon. And then this, I think this kind of explained. Oh, I did not put the explanation there. All right, so I will keep this as a question, and I will explain this in maybe next lesson. So the validation area, actually it's controlled not just by the complexity of that hyperparameter, it also conditioned on your it's also conditioned on your, let me see if I have that in my slides. So I'm trying to actually introduce you the third sanity curve. So the plot of training and validation score, it's not just related to the complexity of your current model, it's also related to the size of your training data. And this third curve is you have x-axis at the training size, you plot the train curve, and so the validation curve. The distance, that's really the distance of this train score and the validation score can tell you, do you have enough training data for your current model choice? And this is the third sanity graph that people use a lot. And we will talk about, I think maybe next class. All right, yeah, this is it. Thank you.